Hello, my name is Jeff Shaw. I'm here today to give a summary of my research over the last semester. Today, I'll be focusing on text mining. Now, within that field, there are several subfields, such as extraction, information retrieval as well. And there's also one important stack in text mining, which is natural language processing, or NLP. Now within there are even more subtasks, but today we're going to be talking more about them. So to start, I'll give an overview and definition of some key terms. Then, I'll give you a timeline on the history since antiquity, really. Following that, we'll do some named entity recognition, and then the application to the biomedical sciences. And then we'll have some tools of the trade. So, what exactly does text mining do for us? Well, there's tons of text-related information out there. For example, on PubMed, there are over 26 million citations. So you can imagine how many words that eventually adds up to. Naturally, humans couldn't read all of them. Therefore, we need to come up with some kind of automated system or process for it. There's one person named Sturdom, he's a lawyer. He said that 90% of everything is crud. So, imagine if 90% of everything out there really is crud, humans would have to waste such an amount of time and energy looking for the specific 10% that they need. So we need to expedite that process to make it easier on the human burden. So we leave things to the computers to do the dirty work. One great example of this is IBM's Watson computer. Now, I'm a huge Jeopardy fan myself. So this is really exciting for me to see IBM's Watson actually beat Ken Jennings. He's on $77,000 worth of questions. So for us, that's a good example of text mining. So, text mining. It's a very broad term, and there are several interdisciplinary approaches taken, such as computer linguistics, or computational linguistics rather, artificial intelligence. There's plenty of different fields that come into play. One term that comes up is text analysis. And that's typically used in the business world. They're more interested in text mining for business intelligence. Companies want to be able to analyze financial reports or any other secret stuff that they might have within their business. And that's an attempt to see what their next move might be. So you get a natural language document, and it's a human readable text. And what's done from there is an output on relationships, structure, data, insights, those kinds of things. And you can see a more formal definition on this slide. It's just one definition of many out there. It's from the Oxford Dictionary. So, and you can see with this graphic, text mining really is interdisciplinary. There are so many fields that come into play, like data mining and database management. There are even library sciences and computational linguistics, artificial intelligence, statistics. Obviously, text mining pulls a bunch of different fields together. We have 7 practice areas here. So, for example, information extraction or natural language processing. The 2 things that are in red here that I've circled are what I'll focus on today. But, to be fair, when we talk about things like extraction, we're going to be looking at all of these different fields. And the history of text mining is really interwoven across different disciplines. But I'll be focusing most of my presentation on NLP. So, natural language processing, or NLP. Human speech and writing isn't always precise. It's very dependent on context. And oftentimes, it's rather ambiguous. it takes a special mind to figure out what exactly is being said. So a computer can easily misunderstand if you just feed our natural language into it. You kind of have to train the computer and understand how we structure what we say. So in that way, it is artificial intelligence. But I wouldn't call it completely artificial intelligence. I would call it a weaker AI. And what that means is that it's focused on completing one task. And that task is to extract the structural information from the non-structured source. And with NLP, it's a field that could be used by text miners, as well as other fields. Now within text mining, NLP is a tool for those miners. And we can see another formalized definition on my screen here. Now there are plenty of subtasks within natural language processing, like sentence boundaries and the detection of them, being able to see where a sentence starts and ends, such as, "No, Mr. Bond, I expect you to die." In that first example, you may not realize where that sentence is actually supposed to end. The period after the word Mr. may actually confuse a computer if you teach it a basic rule. So instead you need to contextualize with some clues, such as if you see two letters before the period, maybe that would be a cue to say that it's not the actual end of the sentence. You might have to look at the other boundaries with some clues to teach the computer. Now if we look at tokenization, the next example on my slide here, the example sentence here is the patient took 10 milligrams a day. And what we have to do is extract the milligrams slash day, not just milligrams and slash and day in isolation. Instead, they have to be together. And there's parts of speech tagging as well. Say if a word were to act as a noun or a verb, those are different and very important in identifying relationships between parts of speech. There are a few other tasks you'll see here on my slide. And one important one for NLP is named entity recognition, or NER. That's going to be the large focus of my presentation tonight. So let's get to that. So information extraction, let's talk about that a little bit. We have unstructured documents that need to have structured information extracted from them. The natural language documents do not have that structure. So what we do is use named entity recognition as well as relationship extraction. And we have this formal definition on my slide again. So let's talk a bit about named entity recognition. We need to be able to identify words that are the names of things. Maybe it's the name of a person, or maybe it's the name of a location. It might be the name of an organization. So for example, we see this on my slide. John went to Wegmans yesterday. A named entity recognition trick would be tagging the names. So an IT kind of classification would look like John being tagged as a person, and then Wegmans would be tagged as a store or a location. So that's part of NLP. And then we have a biological example on the bottom of my slide. We have amoxicillin, which would be the name of a drug, and then E. coli, which is the name of a pathogen. So when there are things that are identified as names, we try to look at the relationship between the words and the names. That's really what we're getting at. Now, we need to measure performance with three very important measures that have been in the literature. We have precision, we have recall, and we have F measure. Precision is the ratio of true positives over the group of things that I identified as positives. So the ratio is between what is right over what is identified as positive. With recall, we have the true positives, which is the ratio over what is actually the reality, in reality positive. And the F measure is a harmonic mean. The F measure is a weak inverse relationship between recall and precision. So if recall is high, precision tends to be a bit lower. And we can see that in this graphic here on the bottom of the slide. Now, way back when, the graph would be a little bit more curved inward. But now we see that that arch reaches out. And that shows that we've developed or made improvements. So we'll move from our overview, and let's look at a timeline over history. Now, I want to warn you all, this is not a comprehensive or perfect timeline in any way. This is just to kind of show the path of research. So if I had more time to actually focus on it, might be a better timeline, but we'll see what we got. So, like with all science, we have to start way back when in the very beginning. If you'll see here, we have Plato and Aristotle, two very well-known philosophers. Plato had the idea that words are innate. It's something that cannot be learned. If you were to see water, you just say whatever sounds right and leave it at that. Now, Aristotle disagreed with that completely. Aristotle felt that language is deductive, like physics. The word is graded and assigned to the object. It doesn't matter if they are connected in any way, it just is, and that's what you call it. Now, prior to the 1950s, we have some other ideas that start to form, like with Thomas Hyde. He was the first librarian to create a catalog that actually classified or by category. So if there were books that are about religion, they were put in a certain section. If there were books that were on maybe kings and queens in history, they would be put in another section. But prior to Hyde's work, they were categorized by name of the author or the title of the book. So this is the first person, Hyde, to really think of those kinds of categories. And then, of course, we have Dewey, who worked much further on that idea, and he has that very well-known decimal-based classifying system. And then we have Shannon, lastly. That is considered the father of mathematical theory. So there's a model of communication that looks at the source, which is then sent through the transmitter, as we can see, into the channel, into the receiver, and then finally into the destination through that chain of command. Now, his idea really was seminal for the rest of our field. If we move forward into the 50s, we have two very key people here. We have Luhn and Chomsky. Now, Luhn tried to develop a system for business intelligence. He wanted to automate abstracts, which were any kinds of documents, or maybe they were reports, something that was important for a business. So Luhn came up with a very basic method that was pretty much based on statistics and the significance of the individual sentences. And Chomsky, well, you all know him, very well-known linguist. He wrote one book called Syntactic Structures, and he thought that all language was universal. Chomsky felt that language could be, or is, rule-based descriptions within each language, and that each language had its own syntactic structures that followed a common theme. Chomsky was very controversial, but his ideas are still useful to this day. If we move on to the 1960s, we see things starting to become a bit more advanced. So, For example, with Weizenbaum, you can just read through that little chatterbot on the side. But it's essentially a computer psychiatrist. So you can see here it says, "Hello, my name is Eliza." And the user says, "I am afraid." Then the computer asks back, "How long have you been afraid for?" And you can read through. So that last sentence, "Do you enjoy being afraid of failing your courses?" doesn't sound like a very sensitive psychiatrist to me. But that's actually a huge jump for natural language processing. We see the beginning of concept extraction and usage. Maybe it's not fully comprehensive or sensitive necessarily, but we see that beginning understanding of conceptual usage in conversation here. Also, the system for biomedical sciences is also being applied at this time with Pratt and Packek. They thought that they could generate a system that could run medical reports and health reports. They came up with the idea of kernel phrases, and later that becomes an idea of that later becomes entities. Now in the 70s, there were a few pretty major jumps. So we first have Codd, who published the paper in 1970, who essentially created databases. That was a huge jump in databases, because now we were able to change databases to see what we were actually interested in and generate that information. So that leads more into relationship extraction. Another important person is Salton, his 1975 paper. He introduced two different models. One was the vector space model, and that changes sentences and words into vectors, which allows us to treat those in quantitative ways. He also showed us the TF-IDF scoring, which stands for term frequency inverse documentation frequency scores, which basically looks at how much content one word can provide. Then in 1980, we see some more discoveries. We have Swanson. Swanson wrote a very interesting article in a liberal arts journal, oddly enough. No mathematical ties, but we see that there's a lot of unidentified knowledge out there that's within our literature. And Swanson thought maybe we could use computers to actually extract the unknown knowledge. And that was an early example for the realization that we could use unstructured texts to find new ideas. If we see Friedman up here also on the slide, and Shapiro, we see the beginning of applications for information retrieval and extraction to medical records. Those were somewhat successful, but not quite there yet. The ideas were really innovative and started to take form, but they weren't applied yet to biology. They still stayed within the medical domain. Now, Hafner, in '94, had a piece that was really the first time that someone came to the realization that this could be applied to biology, molecular, micro, or otherwise. So we had this turning point where we saw NLP and text mining possibly allow us to do better analyses. At that time, that mining was really blowing up and publications were flying out the presses, but it was impossible to actually read all of them as an individual. So computers were actually able to help us with that sifting process. There were already domains that had realized these kinds of things, such as business and medical, and that they were so helpful. And then biology began to develop their own NLPs. And another important development was done by AppDay. That was the first application of domain trees in learning, in first usage of decision trees for classification. Essentially, it would categorize words and tie them into larger Now, in the mid-1990s, things really started to pick up. For example, we have Cortez and Vapnik. They invented the support vector network, which was really a key algorithm for learning text classifications as well as named entity recognitions. Then we have Grisham and Suntime. They presented at a conference called Message Understanding, and that was supported by the military. It was about learning things from military reports or information reports, as well as the movements of the enemy and terrorism. So this is named entity recognition. Now the idea wasn't new, but we finally had a name for it. So it's pretty much what I've shown you in the past, but now with this formal name. And then we have Fukuda, who I believe, as far as I know, to my knowledge, it was the first time we saw NER in protein names. And that was in '98, which is fairly recently. Now, in 1999, you may wonder why I picked that year specifically, but it's because there was such a surge in publications as it related to NLP and biology, and text mining in general, really. Those 3 articles may not be good representations of 1999. They were just 3 of the many, many publications. So we see the first example here is Blausch, and that's the relationship of information extraction. We already had a good idea of named entity recognition, but now we need to find the relationships between the names and entities, and refine that a bit more, which is what Blaschke did. And then, if we move on to Tanabe, there was a release for the, internet access, which is a lot easier, although it was an older version of what we know to be the internet. But essentially, it was able to search through genes and find the relationships between genes. So that relationship extraction was really picking up towards the turn of the millennium. If we move forward to the early 2000s, we see extreme growth with Friedman. That was with the release of Genies. And it was essentially an all-purpose tool to extract information from genomic literature, or biological literature, really any type. Then Collins and Duffy in 2002 published a paper that tried to improve the use of decision trees, to make them faster and more efficient. And after that, decision trees became very popular and really picked up, as well as just being more efficient. In the late 2000s now, the most important paper probably was done by Ratanov and Roth. And we saw that statistical methods were better for NER. Now, up until that point, NER was based on rules created by humans who had to continuously tell the computer what something means. So we might have to say for a protein, it looks like a capital letter, a lowercase letter, followed by a capital letter. So those rules were essentially proven to be less efficient than what Ratanov and Roth came up with, which used statistical methods. When people read that piece, they realized that NER had to move to more statistical and machine learning methodologies. Kralinger invented a very successful annotation system, which was able to find points in the data that could actually point to references. essentially backtracking between data and reference and pointing to one another. I believe that they use HMMI, hidden vector model. I'm not completely sure about that, but we'll talk more about that later. Now, 2010s. Still very difficult to tell which papers will be the most influential and which are just going to fall by the wayside, but currently we have Colbert, who had the idea that we should drop the supervised NLP approach, which essentially gives the computer training data that is already labeled. Colbert wanted to move past that because the labels, require a lot of work and time, and instead we could just give a direct label and have the computer learn it. His paper had a lot of citations and a lot of support, but the idea hasn't quite taken just yet because of the lack of supervision. Maybe it will eventually. Then lastly, we had Zhang, who came up with the idea that we should move past the supervision and focus on unsupervised work. So that's just the general trend for NLP and NER, to eventually become unsupervised and use neural networks because we can. And it will also allow us to have different languages included as well. I mean, of course, we see that English is the dominant one right now, but it can include papers published in Chinese, Russian, and other languages. Now, full-text articles, way back when, we started with abstracts because they're shorter for information extraction, so they're easier to actually read. But for full text, there's more information, but it's less dense. So that was a major problem that we're still working out. There are a few competitors still going on, like BioCreative. There's some challenges that we're trying to address, like how do we solve a certain problem and so on. There are some tools that I will talk about more and look at the results of those competitions. There are also still some, unresolved problems, such as the evaluation in clinical contexts. Something may not be successful in a clinical context, but a doctor may be using words interchangeably that may not be programmed, so we need to have, a human evaluation is easy, but a computer's evaluation is much more difficult. Then there's also the curse of dimensionality, which has been a problem since the 1940s. And we see this visual on my slide, but essentially, if you drop a penny on a football sideline, not within the field, but on the sideline, you can find it pretty easily. But if you were looking at the entirety of the football field and you just kind of threw it in a random spot, it could take you a while to find it, of course, right? So if you take that football field and you make it a football cube or a football society and it's got more dimensions, it would take you forever to actually look for the penny. So that's the problem of dimensionality. If the data becomes more high in dimensions, the algorithms will struggle that much more. So we have to find ways to reduce those kinds of dimensionality ideas. So that's it for our timeline for today. Let's do I'll let you process, so take 1 second, grab a drink of water. So let's move on to named entity recognition, and as well as some technology and uses. So this is a workflow of text mining as it relates to extraction. So we start with the raw text, and it's broken up into sentences. They are tokenized, which means that we pull out usually just words and then have blanks bracketing them. So we have parts of speech that are tagged, and we now know what parts of speech those tokens are, and we can better recognize what entities they are. If it's a person, if it's a location, if it's an organization, or a time, or a protein, or a disease, or whatever it is, the entities are directed. Then what we do is find the relation between the words, not the things, but just the regular relationships between the words. like affects, or activates, or inhibits. Those kinds of terms are then bound and then thrown into the database. One important tool for NER is lexicons. It's not necessarily a dictionary, it's not really a thesaurus either. It's essentially a list of words that are grouped by category. And it's helpful to just use them to directly name a group of things. But it's also beneficial for helping with words. So for example, if you were to see MS, like Ms. or Mr. or Mrs., we know that there's another word for naming that thing. So it's a helper word, like a protein or a gene. It helps us better know what that subordinate is, to give us a better idea of where this term comes up. And then you can see a popular picture of the lexicon here. So now you kind of know what that apple looks like here. You see the idea. Now there are a few approaches for NER. There's one that's rule-based, which we talked about a little bit, where humans have to tell the computer, you know, the protein name is a capital, lowercase, lowercase, capital. That would be a rule that you could teach it. But it's a lot of labor and work that goes into it, but it's easy enough to accommodate, which is nice. It's just a lot of work. Then there's supervision, which is where we have the computer label the data. And then there's semi-supervised, which is bootstrapped. So we have a small set of labels and data that will eventually go from there. And then lastly is unsupervised. That tends to use clustering. So we have measurable concepts in different areas that are large unlabeled corpus. So these are some examples of the entities in the first graphic. And there's a visual relationship of the extraction at the bottom. The purple is the entities, and the yellow is the relationship between them. So supervised NER has a few different approaches. There's decision trees, there are support vector machines, there are hidden Markov models, there are conditional random fields, and lastly, and conditional, excuse the interpreter. So, one thing about the supervised NERs are that they're categorized by an expert in that field for training data. So, a decision tree. Let's look at this a little bit more. The goal of a decision tree is to find a split point. Wherever those things are split, they'll be heterogeneous. Rather, homogeneous, excuse me. So let's say, for example, with this sentence, is something heavy? Either yes or no, and then they're broken off into those places in a very binary way. Most decision trees are very binary. So one author here, Quinlan, in 1986, invented a very, very important algorithm for decision trees called ID2, which is iterative dichotomizer 3. That was a way to figure out what the splitting points used and how to calculate how much information was needed to minimize the entropy of the information. So, when they're split, whatever created the most information gain and reduced the entropy was good. And then pretty much ignored the rest and attributed that to whatever was left over. Once it's been decided that, you know, it's heavy, it'll move past it, and then focus if it's not heavy on horsepower, say, like in this example. But be forewarned, with machine learning, you kind of have to overfit. I can't really explain this. I'll be better in words. It'll be better with a picture, really. So if you can see here those green lines in the bottom graphic, they're kind of squiggly all over the place. And there's no clear perfect separation. They overlap in some ways. So it's difficult to actually try and parse them out. But you do have to be accepting of the fact that there'll be some overlap. It'll be more robust, it'll be more general. Now, support vector machines. These are one of the most popular models today. And essentially, it's labeled training data. There's something called support vectors, which are essentially lines so what we do is we use a hyperplane. Now, most data are multidisciplinary, which means that it's not, rather multidimensionality, which means that it's not 1, 2, or 3D. There are several other dimensions, which means that we need a hyperplane. Essentially, it's a hyperplane for a plane for the higher categories in order to classify them out further. So support vector machines are looking at hyperplanes that maximize the margin. So if we see a high D, it's not good because they can't be separated out. Rather, H1 can't be separated out, but H2 could be separated with the black and the white, but there's a very small margin. In the future, the data might fall past that point. But if we look at H3, we have the maximized distance between those two. So when future data points come in that are unlabeled, we'll probably be able to have them fall into either category. This was also invented by Mercer a while back, 1903, or rather 09. He invented something called the kernel catcher, which is when data is in a low spot and really can't go anywhere, like within this bottom picture on the left. It has to be transformed into a higher dimension to make it cleaner and easier to separate by hyperplane. So we have hidden Markov models here, and they first came up in 1997. The idea was that the original text would have the citation and label pairs, but the labels were thrown out and essentially hidden. They really didn't even exist in the first place, to be quite honest. It was more of the theory behind them. So how do we pull those labels? For example, in this graphic, the top bars with those Ys, that's what we see, the words. But they have these secret labels which are in the bottom of the picture. You have to find those labels, and it's a really complex process. Quite honestly, I don't necessarily understand it myself, but I'm working on it. This is just the general idea of what this looks like. And it's an algorithm that was written by Vertibye, and it calculates the probability of the label for each of the observed pieces. Now we have conditional random fields, which are built on the idea of HMN. That's how we look at different points. So if there's a point nearby, and I don't know, let's use this example. Say it's a part of speech like an adverb, and then another point is a noun. There's a label within the data to say which is most likely to be. So if there's an adverb, it's most likely that the next word is a verb. Such as, he quickly ran to the store. So an adverb typically is tied to a verb. And what they essentially do is use probability to figure that out. The same idea applies to named entity recognition. So it creates a function for each sentence, and it also labels it. Lastly, it weighs it by the interest, and transforms it into probability, which is a lot of math that comes in here. Now, relation extraction. This is defined as a tuple. It tends to be binary, meaning 1 and 1 that then have relationship. So protein A activated by protein B, but there are a lot of matches. So say you were looking for a certain word pair. Like you're looking for is A. You would have two entities, is and A, that need to be found. And then they're put into a table like this. Now sometimes it'll rely on ontology. Most relationship extraction is still in infancy. Recognition is much more mature, definitely, as far as relationship extraction, or in comparison to relationship extraction. Excuse the interpreter. Now, ontologies are knowledge that have already been organized and the computer has already understood. So, information extraction relies on ontologies. But you can also use information extraction to build these ontologies. So it's essentially a positive feedback cycle. The more that we have extracted information, the better our ontologies can become. The better ontologies we develop, the better information extraction we can conduct. So it's a cyclical process. The feedback loop will continue, and soon we'll end up with a very good ontology and a very good set of structured information. Here are just a few famous examples, like gene ontology, where we try and put the connections between genes and functions. All right, so I will talk about biological and biomedical applications. This is an old example by Fukuda. Fukuda came up with a way to extract protein names, and that was based on hand-created rules. So you can see the rules are written out right here. That's what they are, and nothing else. Right there in text. Which they're pretty good as far as precision and recall are concerned. But how much work does it take to actually figure these rules out? And figuring out the order of them and actually applying them? So you can see where there are some issues with rule-based NER. It can be very frustrating to get to the nitty-gritty of it. But it is accurate and successful. It's just if you're willing to invest the time and effort required. And most people aren't willing. Genies was done by Friedman. And that's information extraction in cellular pathways. So we already have that definition for pathways, like knowing that a path is metabolic or knowing that a path is anabolic. So this relates to NER and sentence parsing and medical literature. Very precise, but not so good at recall. Remember when we had that graph before earlier, and it had the inverse relationship between precision and recall? The better precision, the worse recall, and vice versa. So that's where that comes into play here. Now, Textpresso was very popular back in its time, the early 2000s. And that was based on ontology of Genie and Go, or rather gene ontology, or GO. So it was done on regular expression, which means that humans were still creating them. It was not yet automated. But it's nice that it could actually extract the information from biological literature. And you can see some of the categories here. And you can actually see the rules on the right in the third column. It's very frustrating to actually conduct. It would be nice to have a computer that could automate and create those. Now, this is one of the early examples that started to really automate the process. So what it would do is use NER to find words of significance, and I think I talked about this a while back in the semester, but it uses the clusters in an effort to find words that have similar scores in order to create clusters that are more likely to be related to the word itself. This is new, the Chilibot. Well, not that new, actually, my bad, 2004. But it looks at recent relationship extractions, and you can see the map of the relationships with those green lines at the top. It's interesting because it actually follows this, scale-free topology. That means that it follows the real network, not just a random generation, which I think is good. Oof, time is running out, but 90% recall and 100% generative hypothesis, which is good looking back at this study. I see the tools from that time really are starting to mature in the modern age. This is another cool one. This is about social media. And it's nice because oftentimes people complain about the drugs they take on Twitter. And this is actually here. You can see what it does is actually use the name categorization, such as schizophrenia, and it recognizes it as a name of a disease, or anxiety, or tremors as a symptom. So what it does in an unsupervised way, which is a much newer invention, is extract the concepts and allows doctors to get an idea of what's going on out in the world with patients. And this is the actual response to one of those challenges we talked about before, ChemDiner. So it looks at the chemical names and patents, and it uses NER with knowledge. And you can see that the measures do pretty well, about 90% overall. Could be better, but Now, I will close with some tools of the trade. Corpora are a set of labeled texts, documents, which allows one to compare solutions to see if they're in the same corpus. And you can compare the remedies to see which is better. But what we use is the gold standard of corpora, which means that it's already been labeled by an expert and has strict rules outlined. And there's a table here of different corpora that are still used today. You don't have to read it, it's just there. Now this is the more important table. It shows the different tools for name entity recognition. And each column is for a specific type of entity in the biological domains, such as genes and proteins, or chemicals, or diseases. The part that we want to look at are the models. And you can see that most of them use CRF. Other models like HMM, or decision trees, or support vector machines are kind of pushed to the wayside. Now it's all about CRFs. And this is a comparison of the tools. Some named entity recognitions perform well, about 90% mark. Most are above the 85%, which is nice. So NER is definitely maturing, just not quite an adult yet. We have a lot of people in the literature saying that we need at least 95%, but really 99%, 99.99% would be best. So in order to compete with humans anyway, it's already competitive with some lay people, just not quite yet with the best of the best. So here are my rolling list of references. I had too many to actually fit in one slide. So that's a lot of references, I know. You can just click on the link that I've put in this slide, and you can actually see the full list of my bibliography. So, in short, my key points for today: text mining has a lot of fields that are involved, and information extraction
as far as biology is concerned, was developed later on in the 90s. It's still a young field in biology. It's an even newer, even though biology is a much more mature field. Business intelligence already has NLP mastered, such as with IBM's Watson. Yep, they do very well. Google's doing great. So those realms are much more covered than biology as it relates to this. NER is a subtask of IE, but what we really care here about is the relationship extraction in order to help us get a better hold on what's going on and help us discover undiscovered knowledge out in the literature. So we do need to find those relationships and extract them based on named entity recognition. So thank you all very much for listening. And if there are any questions, I'll take them now.